Hey everyone, welcome back. Ever wondered why some of the smartest tools in data science can sometimes backfire when applied to classic statistical methods? Today, we're unraveling a surprising twist in the world of economics and machine learning, specifically, why using AI in a tried-and-true method called two-stage least squares, 2SLS, can actually worsen your results. Let's dive in. So picture this, you're trying to figure out if more education leads to higher earnings. Sounds simple, right? But here's the problem. People who go to college might also have traits like ambition or family support that boost their income. That means the education variable is endogenous. It's tangled up with other factors. To untangle this, economists use 2SLS, a two-step process that acts like a detective. In the first stage, you find instruments, variables that affect education but aren't directly linked to earnings. Think of them as clues, like proximity to a college or tuition costs. You use these to predict education levels. Then, in the second stage, you plug those predictions into your earnings equation to estimate the true causal effect of education. It's a clever way to isolate cause and effect, but here's the catch. What if we use machine learning, ML, to do the first stage? ML is amazing at prediction, so the idea is, better predictions equals better estimates. But a new study shows this isn't always the case. Let's break down why. First, forbidden regression. If you use nonlinear ML models, like random forests or neural networks, in the first stage, their predictions might not play nicely with the second stage. It's like using a recipe that's too complex for the next step. Your final dish could be ruined. Why? Because 2SLS relies on linear relationships in the second stage. Nonlinear predictions from ML can violate this assumption, creating a mismatch that biases your results. Second, overfitting. ML models are so good at fitting data that they might capture noise instead of the real signal. In the first stage, this means your predicted education levels could be too precise, leading to biased results in the second stage. It's like using a ruler that's too sensitive. Tiny errors multiply and mess up your measurements. For example, if an ML model picks up on random fluctuations in tuition costs, those errors propagate into your causal estimate, making it less reliable. Third, exclusion restrictions. ML doesn't know which variables to ignore. If you let it choose instruments or controls, it might accidentally include factors that shouldn't be there, introducing bias. Think of it like letting a robot pick ingredients for a recipe. It might add something unexpected and unwanted. This is especially dangerous because 2SLS depends on strict assumptions about which variables are excluded from the second stage. The study tested different ML methods. Linear approaches like post-Lasso and principal component analysis, PCA, worked well, matching or even beating traditional OLS. But nonlinear methods, they introduced more bias than plain old OLS, sometimes even worse than ignoring endogeneity altogether. Why? Because nonlinear models often overfit, violate linearity assumptions, and fail to respect the exclusion restrictions required for valid instruments. So what's the takeaway? ML isn't a magic bullet for 2SLS. While it can help in some cases, it's a double-edged sword. The key is understanding the trade-offs. Simpler methods like Lasso or PCA are designed with these causal challenges in mind. They balance prediction and bias more effectively. But here's the surprise, even traditional methods aren't foolproof. The study identifies three critical issues when using ML. 1. Noise in predictions that still correlate with hidden factors. 2. Overfitting that reintroduces bias, and 3. Stable but narrow predictions that magnify errors. In the end, the best approach is to combine the strengths of both worlds. Use ML for tasks like instrument selection or feature engineering, but rely on simpler models for the final analysis. After all, in causal inference, precision without validity is just a mirage. Thanks for watching. If you want to dive deeper into the math or see real-world examples, check the links in the description. Stay curious and keep questioning the data.